Welcome
All
back,
right.
everyone. I hope you all had a good break. Three new faces as organizers here. Alvaro, Matilda, and I will be taking over from Nicolo, Nicole, and Marco for the coming period. And today we'll begin with a talk by Hamza Ahmed, and it's titled T-duality and flavor symmetries of heterotic little string theories. Please take it away.
Hello, everyone. Happy New Year. Of course, first I would like to thank the organizers for giving me the opportunity to speak here, and hopefully we can start this year's string pheno seminar series in a good way. So today I'll be talking to you about this work titled T-duality and flavor symmetries of heterotic little string theories, which appeared in the arXiv a couple months ago with Paul Constantine Ullman, who's a postdoc at Northeastern, and Fabian Rula, who's my advisor and a professor at Northeastern. So let me first just flash an outline slide. So I'll begin with some general motivation and review, in particular of what little string theories are, what are heterotic LSTs, their T-duality, and how one constructs them via F-theory. Then we'll move into the results portion of the talk, where I'll try to illustrate some of the results we had via some examples. And then in the last section, I'll just give some conclusions. All right. So why does one consider little string theories? I guess what's most relevant for this audience is the fact that these 60 theories are a subsector of every 60 supergravity theory with at least one tensor multiplet. However, these theories are more tractable than the full supergravity theory because in particular, gravity is decoupled in these theories. And so these theories can then admit global symmetries, and of course, higher form global symmetries as well, which makes them, which gives us certain constraints that we can put on them. And in particular, the higher form symmetries that we'll consider will be the two group symmetries. I'll explain what that means, and the zero form, the conventional flavor symmetries. However, even though gravity is decoupled, these theories still have an intrinsic scale, much like the Planck scale. And so these theories also admit conventional gravity-like properties, such as T-duality. And for us, what T-duality will mean is simply that, say you have two 60 little string theories, you put them on a circle, the effective 5D theory will be the same, modulo some movement in the Coulomb branch modular space. So now one can use this property of T-duality for these theories to study them. And in particular, one can ask, what is the structure of the landscape of T-dualities for these theories? And in particular, one can also ask, are there any invariants that one can identify on both sides that do not change under T-duality? And there's been some recent progress along these lines and other directions. In particular, this started with the classification of these LSTs via F-theory back in 2015. And then this geometric construction was recently used to, as I said, match certain invariants across T-dual LSTs. And furthermore, recently, the Higgs branches of these theories have also garnered a lot of attention. Of course, however, there is much more to be explored. In particular, a question that we'll focus on will be the T-duality in the presence of non-trivial holonomies, which I'll explain what that means. Then, of course, one can also try to figure out if there are other invariants that need to match across duality. And finally, one can also ask what happens if we allow for discrete twists along the circle compactification. And of course, much more. So, but for the purposes of this talk and this work, we will focus on the first two questions here, although we have some future work coming up that addresses the question of twisted T-duality as well. So let's start with basic intro to little string theories. So since we'll consider minimally supersymmetric LSTs, the best place to start is minimal 60 theories in general with at least one tensor multiplet. So these theories admit a Dirac pairing matrix which is essentially a pairing between the BPS strings in the spectrum. So this is akin to the direct quantization in 4D. And so these strings naturally couple to the B fields in your tensor multiplets. And it turns out that the determinant of this matrix actually determines for you the UV completion of your 6D theory. And in particular, one of the UV completions is the little string theory. And the others are, of course, the 6D SCFTs and the 6D supergravity theories. And so the LSTs arise as a UV completion when the determinant of this matrix is 0, which implies that you have a 0 eigenvalue for this matrix. And so from this picture, one can sort of see that LSTs are much like the SCFTs in the sense that the gravity multiplet is decoupled. However, unlike SCFTs, they have an intrinsic scale known as the little string scale. So much like the 6D supergravity UV completion. And so basically these are nice intermediate theories between these two other UV completions, which makes them an interesting case to study. So what is the data that one can associate to these theories? So on the tensor branch, one can package the field theory data in terms of a clear gauge theory. And in particular here, let me use my mouse. Here you see the gauge algebras in your theory and their associated BPS strings, which have been labeled by their self-Dirac pairing to the diagonal components of the matrix. And then you have certain matter in the theory in accordance with the 6D anomaly cancellation conditions. So here you have bifundamental matter, and here you have just normal fundamental matter, which then leads to certain flavor symmetries in your theory. Now, as I mentioned, for 6D theories, for 6D LSTs, you have a 0 eigenvalue for this matrix. And in particular, this matrix also shows up in the Lagrangian description of the tensor branch as coefficients of the kinetic terms of the B fields. And so a 0 eigenvalue implies that there's a linear combination of these B fields whose kinetic term vanishes, which means that which means you have a non-dynamical B field in the spectrum. And so this non-dynamical B field can then generate for you a U1 global one-form symmetry. And the coefficients of this linear combination are known as the little string charges. And these will be important in computing certain quantities, as we'll see. Furthermore, something else that's cool about these theories is that this one-form symmetry can non-trivially mix with the conventional zero-form or global symmetries. And in particular, the ones we'll focus on will be the mixing with the Poincare and the R symmetry of your 6D theory. And this mixing is essentially coded in these coefficients here, given by kappa R and kappa P. And they turn out to be certain mixed global gauge anomalies in your 6D theory. All right, so now let's focus on heterotic LSTs in particular and their T-duality, which is the focus of course, this work. So one has a little string theory associated to each heterotic string. So for the E8, each supersymmetric heterotic string. So for the E8, heterotic LST, one has, this theory arises as the world volume theory of some NS5 branes probing an ADE type singularity. And so via the Mackay correspondence, we know that this singularity takes the form of this non-compact space, C2 mod gamma G. And of course, this is non-compact because, as I said, gravity is decoupled in these theories. And finally, one also, in addition, has a choice of the flat connection for the E8 gauge bundle at infinity. So at the boundary of this space, which is S3 mod gamma G. And this choice of flat connection for your gauge bundle essentially is encoded in the first homotopy group of this boundary. From a physics perspective, all this choice does is that it breaks for you the full E8 gauge bundle. And what's important here as well is that from the point of view of the world volume theory of the NNS5 branes, this E8 gauge bundle is actually a flavor symmetry of the theory. And so we will denote this theory via the symbol here with the associated data. including the flat connections. And these theories also have a nice realization via heterotic M3 duality in terms of the Hrjava-Witten picture. And so this I sort of summarize here in this diagram with the quiver below it. So here, as you can see now, you have NM5 brains that are probing the C2 mod gamma G type singularity, and with certain M2 brains stretched between them. And there's also of course the M9 M9 brains at the end of the interval, at the end theory interval. And so in the quiver notation, we get the following LST. And these self-Dirac pairings are essentially the self-Dirac pairings of the string of the M2 brains that are stretched between the NM5 brains, and also the M5 and the M9 brain. All right, so one has a similar construction for the SO32 heterotic little string theory, except now, of course, you have a choice for the flat connection associated to the SO32 gauge bundle. And these theories were studied very nicely in this paper by Bloom and Trilogator in '97. And in particular, for a trivial choice of the flat connection and a trivial choice for the singularity, one finds an SPN gauge theory with no tensors. And if one has a more complicated singularity type, one gets a gauge theory with SPSO type algebras, and in particular, the shape of the quiver takes the shape of the Dinkin diagram of G, or its foldings. And so this is how in the SO32 the singularity is encoded in your theory. So we know that the E8 heterotic string is T-dual to the SO32 one upon circle compactification. And it turns out that this T-duality then descends to a T-duality of the associated heterotic little strings, of the associated little strings. So let's say we put these theories on a circle, turn on possibly some Wilson lines, and let's say we can encode this sort of map, this compactification plus Wilson lines in terms of these maps here. And so in both cases, you get a 5D supersymmetric quantum field theory. And so now the statement of T-duality is essentially the statement of the equivalence of these maps. And so a natural question that one can ask is, what is the structure of this map? And in particular, what is the structure in the case of non-trivial holonomies? Furthermore, one expects certain data to match just on field theoretic grounds. One of these data is something I introduced before, which were the two group structure constants, which are, as I said, some mixed anomalies in the theory. Of course, one then expects the 5D Coulomb branch to match. Finally, one also expects the number of Wilson lines that you can turn on along the circle to match, which is just the rank of the flavor algebra. However, in the common construction of these theories, which I'll explain in a bit, via F theory, the rank of the flavor algebra is not clear, because the flavor algebra is known to not be fully realized in geometry. And so one of the results of this work was to establish this match via field theoretic arguments, as we'll see. So now let me just quickly review the F theory construction of these theories. So one can get 60 supersymmetric theories by putting F theory on a non-compact elliptically fibered Calabi-Yau threefold. And in particular, the base B2 here of the vibration is non-compact because that's what leads to gravity being decoupled. And so for the cases we consider where the torus fiber has a section, so a distinguished point, in these cases you can represent this F theory background in terms of a Weierstrass model. And so in one picture, this is our F theory background. So just note that the base B2 is non-compact, so it should be infinite, but obviously I can't draw that. But in particular, I would like to bring your attention towards the places where the fiber degenerates over the base. This is what leads to 60 gauge or flavor symmetries. And in particular, depending on which kind of curve your elliptic fiber degenerates over. So if it's a non-compact curve like here, then it would lead to a flavor symmetry. And if it's a compact curve, it leads to a gauge symmetry. Now, what's important here is the intersection, is the Dirac pairing matrix. Now, the Dirac pairing matrix in terms of geometry is encoded in the intersection matrix of the compact curves in the base. And in particular, the condition that we had, which was that you need a zero eigenvalue for this matrix, can now be encoded. It now gives you the condition that there should be a unique curve class in the base with zero self-intersection. And so this fixes for us the base that we want. Particularly for heterotic LSTs, the base is birational to P1 times C. All right. So how does one see T-duality via the geometry? And in particular, in our construction, two little string theories are T-dual if they arise as inequivalent elliptic vibrations within the same Calabi-Yau threefold. And so why these are T-dual can be seen via the MF theory duality. So we know that if we put F theory on a circle, and the resulting 5D theory is the same as if one puts M theory on the same Calabi-Yau threefold. But from the perspective of M theory, the fiber is physical. So from the perspective of M theory, these two theories are related via some birational transformation, which from a physics perspective is just moving in the Coulomb branch moduli space or the Kähler moduli space of your threefold. And so this is how the duality is proven via geometry and MF theory duality. And so in particular, we'll also find more than two vibrations, as I'll show you in certain examples in a bit, within the same Calabi-Yau in our construction. So we use toric methods. And maybe there's more if we construct them in some other ways. So now the matching data that I talked about earlier can be encoded in terms of certain geometric data, which I've listed here. But in particular, for this talk, what would be important is the rank of the flavor algebra, which is just given by the number of non-compact divisors in your Calabi-Yau threefold. And so when one gets the quiver and one writes it down from the geometry, one finds that sometimes the field theory the field theory tells us that there should be more flavor than that which is realized in the geometry. And this is something that's been seen before, that F theory does not always realize the full flavor symmetry of your theory. And so, as I said, one of the results of this work was to establish this match via field theory arguments, because we know via geometry that these theories should be T-dual. All right, so let me get into the results now. So let me just flash the main results, and then I'll try to explain them via examples. So so we basically constructed a bunch of new little string theories with non-trivial holonomies, and also we constructed obviously the LSTs with their T-duals with non-trivial holonomies. We then matched the known geometric invariants that I just laid out, and then we also matched the flavor rank for all examples. And along the way, we found certain interesting little string theories that sort of elucidated some nice properties of this T-duality structure. And so now let me share some of these results in the form of examples, and hopefully make it clear. So let's talk about the flavor rank matching first. So let's consider the following example in the E8 heterotic string with the following singularity. So in the Java written picture, this is just MN fibrins probing a C2 mod D4 singularity with, let's start with trivial choices for the flat connection. So we have the full E8 symmetry. And so this is the quiver we find in the geometry. Now let me just turn on some non-trivial mu1 and mu2. And what we find is the following quiver. And the black ones, the black flavor symmetries are the ones that we find in the geometry, whereas the blue ones are what we expect via 16 anomaly cancellation, but we actually don't find in the geometry. And so when we do the match, we need to take these into account. We need to figure out the flavor theoretic the field theoretic flavor symmetry, and then proceed. Furthermore, another subtlety is the fact that these U1s in general, even though it's not the case in this quiver, these U1s can in general be ABJ anomalous. So some of them may not be actual global symmetries of your theory. and only certain linear combinations may form your global symmetry. And so one needs to compute these surviving linear combinations, and then do the flavor match. And this was done in these references here for 60 SCFTs, and we use similar techniques. And once we do this for all examples that we construct and all their T-duals, we indeed find the flavor rank always matches. And then we have a nice table at the end of the paper where we have a bunch of examples where the flavor rank is shown to match. Now, once that's done, let's now focus on let me show you certain cool examples of that we find that elucidate this nice structure of T-duality. So in particular, consider the following singularity, E6. So like I told you before, that the base topology of the SO32 duals takes for a certain singularity G, takes the shape of the affine Dynkin diagram of G, or its foldings. So a natural question arises is that if I give you the two group data, I give you the Coulomb branch, I give you the flavor rank, and I also give you the base quiver topology. So I tell you what the topology is. Can one uniquely fix the SO32 dual? And the answer is almost. And the reason for this is in particular the E6, the affine E6. Because for affine E6, you have two different Z2 outer order morphisms that give you the same base topology. And these are sort of given here, these two foldings. And so if you do these two foldings, you get the same base topology, which is that of affine F4. And so a natural question is that can we realize both these, so can we find two different SO32 duals that each of which corresponds to these two different foldings? Can the geometry realize this? And so let's see this via this example here. So then this is the E8 theory with some value of mu1 and mu2. And so this is the quiver we get, and you can see here you have the E6 singularity. And now one can look at the duals in the geometry. So one of the duals that we find is given here. In particular, this U1 is the non-ABJ anomalous one that survives, and it sort of goes through the whole quiver. And furthermore, we find another dual in the same geometry, which is given here. And as you can tell, these two theories are completely different. They have different gauge algebra, they have different flavor symmetries. However, they have the same base topology. And this is something we only find for E6, and this is because of this argument of its two different foldings. And so indeed, the geometry realizes these two foldings. In particular, what this example shows is something else, which we find when mu1 and mu2 are non-trivial, is that T-duality is not an isomorphism, because you find two different SO32 duals for the same E8 theory. And this is what we find in most cases. So now let me finally present an example of self-dual theories. And so the motivation for thinking about these is the following. So we know that the SO16 is a common subalgebra of both the heterotic gauge bundles. And so one can ask, can you pick a mu1, mu2 such that the T-dual lambda is such that we get the same flavor symmetry on both sides? Because this seems like a nice place to start if you want to find a self-dual theory, because they have the same flavor symmetry. And then the question is, can you find a singularity such that you get the exact same theory on the SO32 side and on the E8 side? And so indeed, we find such an example for the SO4N type singularities. In this case, the E8 LST is given by the following quiver, and the SO32 LST is given by this quiver here. And so one can check that if we plug in m equals n minus 1, we get the exact same little string theory in both these quivers. So now let me conclude. So in this talk, we established the flavor rank as a T-duality invariant by taking into account certain by using field theoretic arguments. And in particular, this matches with the result in this paper here, where they found the same thing for certain singularity types using other methods. And we also further investigated the landscape of the T-duality map for non-trivial holonomies, and we found some nice features of this map in the shape of self-dual models and multiple T-duals, etc. So now, of course, there's still much more to be done. In particular, can we find other invariants that one can match across these T-dual theories? So that it's more constraining. And then what about twisted T-duality? So you have this picture from before of T-duality. Now, what if you allow a certain discrete twist along the circle by some discrete symmetry of your theory? And we have some first results, which basically show that the structure of T-duality is much more richer. And in particular, we have an E8-E8 theory that is T-dual to a twisted E8-E8 theory. And finally, I guess the bigger question is, what fraction of the T-duality landscape of the full 6D supergravity theory do these heterotic these LST T-dualities cover? And yeah, that's it. Thank you for your attention.
Thank you, Hamza. Are there any questions? If not, I have a quick naive question myself. So you're talking about these global symmetries in the little string theories, and say you were to recouple gravity. Is there then any difference in how the global symmetries are broken between the ones you see from geometry and the ones you don't? How does this precisely work?
So when you recouple gravity, this E8E8 and the SO, well, naively, let's just consider the case where we don't have any non-trivial holonomy. So the E8E8 just becomes the full gate symmetry, and the SO32 becomes the corresponding gate symmetry. In the case where you have non-trivial holonomies, again, I would expect that they would all just become gate symmetries, because the way we construct this is we start from a compact elliptically fibered Calabi-Yau threefold. So this is a background for 6D supergravity. And then we take a decompactification limit. So it actually does come from a decompactification limit of a 6D supergravity. So these theories you can then track in the geometry how these non-compact curves become compact again. And so they would then give you the gate symmetries. Does that answer your question?
Yeah, thanks.